Thanks for coming. Some people have not been able to attend the last meeting for unexpected circumstances. So I'm very glad to present you Pedro Garcia Fernandez, which is a very well-known people from UPC and from now IonSAT research groups. Miguel did the most of the first doctorate GPS that was about the PhD from our US, and has been working very actively not in Spain, not too much in Spain, but especially in Japan. I remember very well when you moved to Japan with the postdoc.
Yeah, that's correct.
2004, 2005?
2004, 2005, yes, one year.
Later on, we were working on the human space science in Munich.
In Munich, yeah.
And I remember some nice papers about this. They went up.
Yeah, in rockets, that's right.
For instance. And it's Oliver Butter.
Correct.
Also, and later on, you taste the industry, let's say, the industry and space industry in Barcelona.
Exactly, yeah, for 3 years.
3 years in startup in the Trinidad Mountain, so maybe you have already sightseeing, so sightseeing there. There is an observatory, an astronomical observatory. Have you seen it? The mountain? So there.
I was working there.
He was working there in the building for 2 years. And later on, you moved to
US.
to JPL, Ocean Lab, Salina, and until May last year.
Yes.
So, I mean, he, as I like to say, he's one of the few humans, let's say, with access to the source code of GIPSY classes. Source code of GIPSY classes is restricted. So, Miguel has been working actively, in particular, for updating the software. And he's going to explain us a summary of his work.
Interiorities of the...
By the way, sorry for the delay, because the delay was motivated. We are transmitting live the conference in JPL. So there are some people who show his interest from Germany, and this is, and hopefully they can follow the conference live.
Okay.
Thanks so much, Miguel.
All right, thank you, Manuel, for giving me the opportunity. So I'm going to present one of the first works I did when I was in JPL. So when I arrived there, they assigned me, they had a ionospheric model in GIPSY, but they had some flaws that they were aware of that. And then they were saying, well, why don't you come here and help us arrange these problems with the ionospheric model. So basically, that's actually one of the first tags. It's basically a model for the second order ionospheric delay that it's now implemented in GIPSY OASIS, which is the software package that JPL has to process GPS data. So feel free to interrupt me whenever you want. So it's, you can either wait at the end or just when you have some doubt, just feel free. Okay. All right, so a brief outline of the presentation. I'll give a brief introduction, very brief, like a 101 basic course on what GIPSY OASIS-II is. Then I'll move on the morphology and definition of the second order ionospheric effect, on why is it motivated, and then how we model it in GIPSY. And then I will talk a bit on the main effects that this delay, extra delay has, which is mostly for reference frame estimation with GPS. And I'll wrap up the talk with some conclusions. So GIPSY OASIS is one of the de facto full chain process. So it's basically a suite of packages, software packages, programs, different programs and tools that allows the user to compute position from start to end, meaning you start with the GPS raw data, then you go through several steps, several programs, then you end up with positions other parameters. I say it's a de facto standard because there are other programs as well. You have Bernice and other approaches. So, but GPS probably is maybe the most known software. It gives some problems, but and it's actively used in the research community. So I know there are some companies that use it for commercial reasons, but it's mostly used in the research community. I believe the licenses for research are free. Commercial-wise, it's more expensive, but if you are using it for research in a research institution, then you're good to go. Some applications of this software is precise point position. So you have a receiver, and then you want to obtain the positions of this receiver with centimeter accuracy, then you would use GIPSY. Then you can use GIPSY for network processing. So you have a network of GPS receivers. Then you want to compute the GPS orbits and clocks, for instance. Suppose you know the positions of your stations, then you can estimate the GPS orbits and clocks. And then you can also do lower orbiter positioning. So you have a GPS receiver on board LEO satellites, then you can process this data and obtain the orbit of the satellite. So actually, GIPSY OASIS is the software that JPL uses on an operational basis to estimate GPL products for the IGS. These products cover GPS orbits and clocks, reference frame estimation, etc., etc. And all the products that a single user would use for precise point position. Basically, regarding the reprocessing campaigns to generate these orbits and clocks, so JPL has done different campaigns to help the geodetic guys to define the reference frame. So the last one was Repro 2.1. I'll talk about that a little bit later. And I was actually actively involved in that project too. So just if you're not familiar with GIPSY OASIS, I'll give you a really hugely simplified process chain. So you will start typically for a bunch of Rhinex files. Rhinex files is a format to store the GPS data. Then you would go through a program that's called Ninja. Ninja, what it will do, it will go through all the data and say, oh, this data point is bad, I'll toss it around. This data point is bad, I'll remove it. This carrier phase has a break, so I flag this break, etc. So then when Ninja is done, then we go into the observable modeling tool, which is QRegress. QRegress, basically what it does is computes a synthetic range based on the geometry, a troposphere model inside the program, and other models, wind up, etc., solar radiation pressure, and whatnot. And in particular, it has another model, which is the second-order ionospheric model. That's what I'm going to talk about. So when the range is modeled, along with the partials, we compute the prefield residuals as well, and then we filter all these equations into the filter module, and that's where we get the positions of the receiver, or we can estimate the troposphere of the receiver, etc. All right, so I just mentioned that within QRegress there is this small library that computes something called second-order ionospheric correction. So this correction is used to model this effect, the second-order ionospheric effect. And I'm going to talk about the intuition or the physical fundamentals of this effect. So usually, when we use GIPSY to process data, we use the dual frequency ionosphere-free combination. So basically, the idea is that we use a linear combination of two frequencies, and then we can remove the ionosphere. But not all ionosphere. We just remove the first order. There is the second higher order effects that we are not able to remove unless we make combinations with more frequencies. But so basically, the only thing we can do is just model it. So we have an equation that describes this effect. So the delay due to this effect is summarized in this equation. And I don't want to go too much into the details. Basically, what I want to mention is it is a constant that depends on the frequency here, and an integral that basically integrates along the line of sight. And integrates what? Integrates the electron density at each point of the line of sight, multiplied by the dot product of the magnetic fields and the line of sight vector. That's the important thing here, because if the magnetic field is parallel to the line of sight vector, then we will add up more delay into the group and more advance to the phase. That's the line here. So basically, we create an advance into the delay if it's parallel, and if it's anti-parallel, we create the opposite effect. So basically, the phase is delayed a little bit here. So basically, what it does is, if you do not model the ionospheric, second order ionospheric effect, basically all the stations would appear north, right? Because you have the effect north here and the opposite here, but it will move the station north. So basically, when you model the second order ionospheric effect, you basically bring your station southward. So actually, this is how the correction would look like in station coordinates. So notice that for most stations, we would have a correction southwards. Now, you would ask why north-south and not east or east-west, and this is basically because the magnetic field has a symmetry around the spin axis of the Earth. So that's why you have this vertical symmetry. And this will have implications when you try to estimate the reference frame with GPS. I'll talk about that later. So now, how we model it in GIPSY? We basically start from the equation we just have seen. And we have to actually make an assumption here. We have to make an assumption because we typically don't know the electron density at each and every point of the line of sight. So we have to make some considerations here. And what we do is we assume that the ionosphere is a thin shell. So it's a shell with infinitesimal thickness placed at a certain altitude, which is typically 450 kilometers. This would define a Pierce point here. That's the crossing between the line of sight and this thin shell. All right. If we work under this assumption, then this expression is the one that you have seen. And just remove the constant and group them here just for simplicity. So basically, the main idea is that under this assumption, we can then separate, on the one hand, the integral of the electron density, and then on the other hand, the dot products of the magnetic field and the line of sight at the point of intersection, at the Pierce point. So then this is what we call the slant EC, the integral of the electron density along the line of sight, slant total electron content, that multiplies this dot product. So now the expression for the correction is much more simplified. So we just care about that point. We don't care about the whole line of sight anymore. Now, we have in GIPSY several things to choose from. So in terms of a magnetic model, GIPSY allows you to choose either a model that's a constant dipole, that's the most simple model for the magnetic field. Basically, it's symmetric along the spin axis of the Earth. Or you can use the more realistic International Geomagnetic Reference Field, GRF, which basically is a set of coefficients from a spherical harmonic expansion that is updated I believe it's every 5 years, and it's much more realistic. And then, on the other hand, for the slant total electron content, we have several choices here. We have what we call the DCV. Basically, DCV means that the GPS measurements would provide us with a slant tech directly. So I talked about this ionosphere-free combination, but then we have this other combination, which is the ionospheric combination, which allows us, by combining the phrases or the ranges, we have a term that is proportional to the slant tech, plus some other nuisance parameters that are the hardware biases. We have to somehow calibrate these observable with those hardware biases. Then we have two other choices, which are basically based on global ionospheric models. We have the one based in Yonex maps. Basically, Yonex maps is a set of maps that are time tagged, and it's basically longitudinal, latitudinal grid, and in each point we have what we call vertical total electron content. So the ionospheric integrated along the zenithal direction. So now, allow me to go back 2 slides. So we have the vertical DC, and then when we know the geometry of the problem, we simply apply a mapping function and then convert it to slant direction. And then the GM-based IRI is exactly the same, but instead of using maps, we use a climatological model, in this case the International Reference Ionosphere. So now we have 3 models to choose from. So what is the correct one? Well, it depends. It depends on the type of application and your restrictions or limitations that you have. So this table basically shows which are the pros and cons. The DCB approach doesn't need any mapping function. That's a very strong point, because the mapping function introduces some mismodeling when we convert from vertical to slant. But on the other hand, it needs to be calibrated. We have to have a DCB or a database of DCB or hardware biases to correct the measurement in order to obtain the slant DC. And we can process any date that we want as long as we have data. So we can go back to 92. If we have data, we're good to go. Now, on the other hand, we have the GIM-based models. They do need a mapping function because they give you the vertical of the electron content, but then you have to transfer it to slant. But it doesn't need calibration because there is no GPS data involved here. But the problem or the difference between these two is that in Yonex, you can have maps up to June 98 that are public. You can find some institutions that would give you maps to 96. But if you want to process before, you're in trouble. And particularly if you want to have orbits and clocks for 92, 93, that's where Topex Poseidon was operating, then you're in trouble. What do you do? All right, then you can rely on other models like the IRI, which is a climatological model, and in principle you don't have any limitations in date. So, for instance, I'll give you some use cases. In case you have ever to choose from it, then you can see that if you're going for a BPP, precise point positioning, where you have to typically process just one receiver, and it's relatively easy to have access to the differential code biases, or you can make a script to compute them yourself, I would go for the DCB approach because it's the most accurate you can have. You don't have to rely on a mapping function, and that's a really, really good point. But on the other hand, if you have to make a network run that you have to maintain operationally, that for instance JPL does, right? They have to compute the GPS orbits in almost real time, or they have to make reprocessing campaigns with a network that changes from day to day, then DCB, it's kind of a problem because you have to maintain this huge database of DCBs for stations that may come in and you didn't have the DCB, and so there is some mechanisms here that prevent you to have a smooth operational runs. So in that case, we go for the Yonex approach. You have maps every day, and when you don't have maps, you rely on IRI, for instance. And that's what we did for the last pre-processing campaign. Up to 1998, we use IRI, and then from 1998 onwards, we use Ionex maps. So now the problem is, with GIM, we need an effective height for the ionosphere. Remember, in the couple of slides I mentioned, yeah, you have to define a height for the ionospheric height, which is typically 450. But there is a problem with this height in this particular context, as you will see later on. So let me put this on hold for a while. Let me now talk about on this major effect of the second order ionospheric effect, which is the shift in the Earth axis, and then I will link that to the question of the ionospheric height afterwards. So when studying this effect and seeing how this effect changes the station positioning or the or the post-fit residuals of the estimates, I've noticed that it doesn't change that much if you apply the second-order ionospheric effect or it doesn't. The main reason seems to be that it's basically a slow varying effect that it's shared among different satellites for one receiver. So sometimes it gets sucked into the clock estimate of either the receiver or the satellites. So in terms of repeatability, it doesn't change much neither. So then what is the main effect here? The main effect basically is this shift in the center of the z-axis of the Earth. So basically, this is a problem when you use GPS to estimate or realize the Earth reference frame as geodesists do, right? So they basically estimate a whole bunch of GPS receivers, and then from that estimation, they build the reference frame. So the way to do that is basically, or at least the way we do it in GPL is, we make a free estimation of the network, meaning we don't constrain any stations at all. So we have what we call a fiducial free solution. Then we transform it to the ITRF reference frame. And to do that, we use this Kelmer transformation, which is basically a bunch of parameters, namely 3 rotations, 3 translations, and 1 scale. And with this set of 7 parameters, we can change between two frames. So now we are just focused not in the scale, not in the rotations, because the ionosphere here doesn't play much role. But the problem here is in the translation in the z direction, which is the spin axis, right? So basically, we have a plot here where you will see the effect. So on the x-axis, it's basically the year that we processed for these reprocessing campaigns. So each point corresponds to 1 day of the z translation, which is in the y-axis. This basically means how much do I have to shift my free solution in the z direction to match the ITRF reference frame, which is typically computed with satellite laser ranging and VLBI. So from now on, ignore the green. We're not interested in the green line. I'm interested in these 2 lines, the blue and the red one. So the red one is the previous reprocessing campaign. So the one that came before Repro 2.1, where we introduced the second order effect. And we see that there is a bump here around 2001, 2000-ish. Then this bump disappears around 2008, which is solar minimum. And then it's ramping up again in 2014, where we are approaching the solar maximum again. So you could see that there is this clear signal that actually depends on the solar cycle. And this is because the second order ionospheric effect. If we instead model this effect here in Repro 2.1, then you would see that this is mostly flat. So basically we have removed this effect. And so this same plot expressed in period rather than time, you would see that, if you remember, the red one was the one without second order ionospheric model. You have large components here in 1 year, 11 years, which are the ones tied to the sun, right? You have the season effect and the solar cycle. That basically these components disappear when you model the second order ionospheric effect here, which is the blue. So now I want to show you these last slides, which is actually to go back to the issue of the shell height. So which is the altitude of the ionospheric thin shell that I should use? So if we use, for instance, the 450, so this is basically the same parameter that you have seen, so the Z translation, with the DCD model, the one that used the GPS measurements, for 450 kilometers of heights and 600 kilometers. As expected, since it doesn't use a mapping function, it's mostly zero. The difference is mostly zero. There are differences because the thin shell defines the pierce point, and the pierce point defines the location at which we have to compute the magnetic model. So it's expected that it's not exactly the same, but they are similar. Now, if we use, for instance, Yonex in this plot, and we compute the Z transition with Yonex using a 450, and we compare it to the one with DCB, we see that there is a constant bias here, like that can amount to 2 millimeters, no less than 1 millimeter here, depends on the solar activity, of course. So if we do the same for 600 kilometers, then we would see that we basically remove the bias. Basically, what happens here is that when we increase the heights of the ionosphere thin shell, the mapping function reduces, and then the slant height is reduced, so the amount of correction that you apply is lower. That's why it's closer to zero. And similar goes for the IRI. This is exactly the same plot as this one, but using the IRI instead of the Yonex. The differences here is slightly lower because IRI tends to underestimate the vertical activity. By the way, 450 and 600 is not like a random number of as you can imagine. So basically doing simulations with IRI, and for this context, 600 actually kilometers is the sweet spot that allows you to have this better retrieval. So basically I'll wrap up the talk with some conclusions. So I'll talk about the second order ionospheric effect in general. I'll just explain that there is this north-south shift of the station coordinates because of the symmetry around the Earth's spin axis. This effect actually causes a problem when you try to estimate the reference frame with a bunch of stations, and it is this translation in the z-axis. I'll talk about how GIPSY implements a model to correct for this effect and which are the implications of it, meaning that you basically remove the signal that depends on the solar cycle, at least for this parameter when you estimate the reference frame. And basically, there is this recommendation of using 600 kilometers instead of the typical 450 when you have to use this correction in your processing. So thanks. That ends my talk. Thank you very much.
Okay, thanks a lot. It's time for questions. Everything very clear?
Yeah, thank you so much. It was very clear explanation. I have just a question, which is just for curiosity. When we were talking about the training model to use, you said when we are processing inputs, we use Ionex because we have no DCBs for all the stations. And this is a problem. But in general, it was strange for me because I can assume that if you have a consumer network and you are computing with this network, you should have everything from stations. There is another reason.
No, actually you're right. So the data is there. So you could try to develop this tool that computes the data on the fly. But in operations, the process is so complex already that it's better not to add this other tool that can introduce another point of failure.
This other tool, what does it do?
Well, this other tool, what basically it does is it takes the measurements, then applies some pre-computed DCBs and reduces the measurements, and then it tries to model the ionosphere with Yonex to remove the slanted component, and then the only thing left is the DCB of the receiver. And then you can estimate the DCB this way. Now the problem is, this is a very easy process to do. It's just a simple script, but the whole operational chain is so complex already that introducing this, even though it seems easy, when you try to make this operational, it's going to create some problems. So and it's way easier just to get the IONX map that it's already available, and just get the vertical TC that you need, and then convert it to something. It's not for impossibility; it's just for practical reasons.
In fact, I had sorry, to finish. Had one question or suggested question related with the question of Jaume, which is, have you considered the possibility of computing using the IONX, as you say, for operational purposes, but not using directly the predicted value for every array, but just using the IONX to calibrate the ionospheric carriage phase ambiguity? Similarly, as it is done with the ranges and the DCBs, because in this way you don't need the DCBs at all, but instead of taking the IONX, which is, as you know, typically provided in a single layer with important errors at low latitude, low elevation, you can use the IONX to calibrate the ambiguity of every arc phase, and then you level, maybe also using an elevation, a generous elevation mask. You apply it to all the arc, and you retrieve something in the middle.
Well, because the DCB then gets sucked up in the ambiguity.
You don't need DCBs because you are using directly the IONX to retrieve the ambiguity without the need of pseudo ranges or DCBs. This is an alternative way.
Yeah, that sounds even though it's not implemented here, but yeah, it makes sense. Nice.
Well, it's that if you have the code from the studies that we did, well, if you align the coupling phase with the logics, you will suffer the inaccuracy of the logics. The logics is not zero in. Then, depending on the region, depending on even on the line of the arc, will lose error. From my point of view, it's much better to use the code in this case and to remove the DCBs.
In my experience, depends on the scenario, because the pseudo range, as you know, can be affected by multipaths. Also, you must level, you must average the difference. So, if the arc is short, this will affect as well to the leveling with the pseudo ranges.
This is unbiased. This is unbiased, and this is the advantage of using
multipath is color noise.
It's color noise, but unbiased.
The subroutine that I have provided to the ES conventions is based on this idea. I mean, I also support this idea, but in my experience, the other approach works in general quite well because.
Okay, this is not the moment.
Have you done the assessment?
We did the assessment.
Okay, we can compare the assessments. So, as well. Anyway, in our experience, we can for operative conditions, I suggest to try also the usage of IONX in the same way that the pseudo ranges and the DCBs with an elevation mask, because as Jaume says, as we commented before, the IONX at low elevation has a greater error, so no problem. You have a long enough arc, you can remove this better case. Of course, if you are in a place far from receivers, you are in the case which is, I agree with Jaume, so in this case, the map is mostly based on interpolation. But if you are on the regions, you have a very nice result. So this is something in the middle, in my experience.
But if you are in one single region, you have the data, then you can use it.
Yeah. So, okay.
Thank you.
Any other questions? We have two more questions.
Okay.
Can you please go back to the slide where you write the carrier phase combination? This one. Sorry. This one. Previous one, sorry. Well, I assume that here you have leveled before with the pseudo ranges.
Oh yes, yeah, of course.
Just to be sure.
No, yeah, because then you would have to with the ambiguity term. That's
So you have
correct.
to have.
Yes.
Ambiguity.
Yeah. Typically, Ninja does that already.
Yeah, I assume that you are taking lightly that it is also done respecting the integer wavelets.
Exactly.
For the integer wavelets.
That's right. So you average the range over the whole arc, then you level the phase accordingly.
Perfect. So, thank you. And you can move forward, please. At the table here. Why do you say here that you need a mapping function for GIMI?
Yeah.
For IRI?
Yes. In theory, yes. I see what you're going. So you could, in theory, simulate the slanting. But simulating the slanting means integrating along the whole ray path. This can be really time-consuming sometimes. So the project we did is, instead of doing that, and in order to use exactly the same machinery that we're using for IONIX, meaning mapping function, etc., we instead simulate the vertical TC, and we do the same approach as this.
You're right. It's something as well. Can
Exactly.
be optimized.
Yes.
Yeah. So, yeah. Thank you.
Great, thank you. Thanks.
No more comments, questions? From people using Bernice or other competing softwares?
Not allowed.
Okay, so thanks so much.
Thanks a lot. Yeah.